Yeah, I'm going to tell you exactly what's going to be on it. This isn't a test. This is like a little bitty quiz. I'm going to tell you exactly. It's separate from that. Oh. It's like
change the date on it? Or?
No, I'm not changing the date. We're still going to have like a test. Yeah, I'm calling it a test. We'll have a test at the regularly scheduled time, which is next week. But this is going to be like part of that, but I'm going to give it on Friday. So I'm going to tell you exactly what it's going to be. It's just a derivation. I want you to be able to derive.
Can we get points for this?
Yeah, that'll be fun. Yeah. It'll count. It'll be like a portion of your 100 points for your exam, or your test, or your quiz, or whatever. The thing next week, right? It's next week, right? Monday, right? Is it Monday?
Yes.
Oh.
November 4th.
Yes. Shoot, it is Monday. Well, that's drop day. We have, or the 5th, I think it's drop day. Yeah. So this will just be sort of like a little pre-test. Yeah. But I'm going to tell you exactly what's going to be on it. That way you don't have to worry about studying that for the actual test. There's just some derivations. I just want you to be able to regurgitate the derivation. Because I think it's useful for you to just sort of get practice in that and doing these type of intervals. Regurgitate, maybe that's a strong one.
I was going to say, that's a strange word to use for to.
All right, so I'm going to go over those today.
Regurgitate.
And the question will be exactly as they're posed in the notes. Okay, so really I just want you to be able to repeat what we do in the notes. Is anybody listening? Okay. Yeah, so we'll have a little quiz on Friday. It'll just be like 15 minutes. I'll just ask you to do one of these derivations that I'm going to do today. So last time if we have like this rotating disk, and it's say rotating with an angular velocity omega right there, and let's say that I just take a little piece of it and I say what is the energy of that piece, right? That piece has a certain velocity, but that velocity is related to the angular velocity by that amount, omega r, and so I can characterize its kinetic energy 1/2 mv squared in terms of omega, and that's going to be 1/2 m omega r squared, which I can sort of rearrange that, and I get an expression for its kinetic energy, and it's going to be 1/2 of mr squared omega squared. Now that mr squared is going to be different for every little piece in this disk, because if I have this piece, it has a certain radius, but if I pick another piece, say up here, it has a different radius. So this term, mr squared, is going to be different for every little element of that rotating body. And that mr squared we call the moment of inertia. And that's where it comes from in this thinking of energy in this way. So this is what we had here, where we say, well, if we add up all those little elements of our rotating body, then we can get an expression for its kinetic energy. But it's going to be in terms of this sum of mr squared for all the little elements, which are all going to have the same mass, but they all have a different radius. All right, they all have a different distance from the moment of inertia, or from the center rotation axis. All right. So we call this the moment of inertia, which is I, and I is defined as the summation of mr squared. It's the summation from I equal 1 to infinity, because you break your rotating body up into an infinite number of pieces. Those are called infinitesimal elements. Times m, the mass of each element, times the distance of each element from the rotation axis squared. Right, so I can call this a differential element of my moment of inertia, and that's going to be r squared times dm. So if I have an object, a rotating body, we'll just take a disk, for example, and then this is my differential element. If I want to know the moment of inertia of that differential element, I'm going to call it di, because it's not the moment of inertia of the whole body, it's just the moment of inertia of that little bitty piece within the body. So that's called di. it has a certain radius, r, and it has a certain mass, not the mass of the whole disk, but just the mass of that little differential element. And so the moment of inertia of that little piece is going to be r squared times dm. All right, so this is the definition of moment of inertia. It's the r squared times the mass of the body. Now, if I want to get this into terms of the whole body, if I want to get rid of this d, I just take the integral of both sides, and so I then is equal to the integral of r squared dm. And that's what we're going to be doing in these next few derivations, is we'll be finding the moment of inertia for several sort of regularly shaped bodies, a disk, a rod, a cylinder, okay? And in order to do that, you have to know how to do this integral. Integrate over the mass elements for each of the bodies, okay? You all done this before? Might have done it in high school calculus, integrating over a body. You'll do it again. So it's fairly important. You get to it in Calc 3, but engineers, you'll do this as well when you go into engineering school. All right, so the units of moment of inertia are just kilogram meters squared, because we get the kilograms from dm. Remember, that's the mass of our little mass element, and then we get meters squared from the r squared. And let's see, if we're going back to kinetic energy, remember we had before that kinetic energy was 1/2 mr squared omega squared. So we get a new expression for kinetic energy, 1/2 I omega squared. We'll come back to this in just a bit, but let me just sort of remind you what we've been doing here is that we've been taking these linear variables, x, v, a, f, and now m, and we've been translating them into angular quantities. So for example, x became theta, v became omega, a became alpha, f became what?
AC.
Torque, right, it became the torque. So it became this sort of angular force or torque, and now mass is going to become I. So remember, mass was a measure of inertia, and then I is going to be a measure of sort of our angular inertia. If I have a rotating body, it's not just the mass that determines how easily or how difficult it is to move, it's also the distribution of the mass. All right, so that's called the moment of inertia.
I have a question. How do you know which one you're supposed to use if you're looking at a problem? Like you got 1/2 I W2 or you got 1/2 mr squared W squared. I mean, if you're looking at a problem, how do you know which formula you're supposed to use? Is there something they're going to ask for?
Like for your kinetic energy, for example?
Yeah.
Well, if it's rotating. So if it's a rotating body, you always use the rotational quantities.
But then, so which of those formulas are we playing into? Okay, so like the first one, you're saying that the kinetic energy is 1/2 mr squared or omega squared.
Right.
What would they be asking for in the problem so that we know that we're supposed to use that formula?
We'll look at some examples, but they're going to be energy type problems. I think it'd be better. I'll just show you some examples in a bit, but it'll be talking about energy. We'll also have problems where it's like conservation of energy, where I'll just have to show you some examples. Sorry, I can't really show you.
Yeah, but just one, because with the other questions, so the other formulas you can say when you're looking for omega angulars.
Right.
So you know what you're looking for. But when you use these, I guess.
Yeah, I'll just have to show you some examples. And the fact is, those problems are all going to be one problem. It's going to be sort of all one problem. I think it'll be clear when we get to it. It's a good question, but let me just put it on hold for a few minutes. Okay. Now, first off, if I just have discrete particles like this, I just have particles that are rotating around an axis.
The big particle.
Yeah. So they're just rotating around that axis, and I want to know its moment of inertia. Remember, our basic definition for the moment of inertia is that I is equal to the sum of mr squared. And if we have regular bodies like a disk or a rod or a cylinder or a sphere or something like that, then I have to add up all the differential elements, and that's where I have to do an integral. But if I have discrete particles like this, I can just treat them as discrete particles. And then I just do a regular summation. So here, how many elements will I have in my summation for this body? I'll have 3. And I just add up mr squared for each of the 3 bodies. So for example here, I have a 3 kilogram body at 1 meter from the rotation axis. So it's going to be 3 kilograms times 1 meter squared, plus I have a 1 kilogram body at 2 meters, 1 kilogram times 2 meters squared, plus 2 kilograms times 3 meters squared. All right, so that's 3 times 1, that's 3, plus 4, plus 2 times 3 squared is 18. So that's 7 plus 18, or 25 kilogram meter squared. All right, so that's the moment of inertia for this discrete particles. Now, likely you could see a discrete particle, a distribution of discrete particles rotating about an axis, and they're fairly simple. You just add up mr squared for each individual particle. Notice here that even though the 2 smallest particles, you might think that they would have the most inertia, or the least inertia compared to the 3 kilogram particle, but notice that they have the least inertia, right? Because the distribution of your mass is very important. We'll talk about this when it comes to angular momentum, but if I'm spinning around in a chair, the moment of inertia is going to describe how easily it is for me to spin, right? So you might have seen something like this before, where if you have your arms out and you spin around, you're going to have, what, a big or small moment of inertia? If I have my arms out, big or small? Big. Why is it big? It is big.
Radius.
Huh?
Large radius.
Right, because you have masses that are out at large radii. And so that r squared term carries a lot of weight in determining your moment of inertia. And if you pull in your hands, then it causes your moment of inertia to decrease by quite a bit, because you're decreasing that r term. And since it's squared, it makes a big impact. And so as a result, it's very difficult to spin somebody if they have their hands out, which is why, like if you have, like you spin around like this, you can see. We'll talk about this with angular momentum. But if I pull my arms in, what's going to happen?
Speed.
I'll go quite a bit faster. Right? And that's because of our moment of inertia. Just a second. I used to be able to spin like nothing. I'm not that old, right? But I feel like my balance is different than it was 10 years ago.
You ballerina.
Okay, ready? All right, so this is for a discrete set of particles. Now, you will not see this on the quiz on Friday. If you came in late, there's a quiz on Friday. It'll just be like the last 15 minutes of class. It'll be one derivation, and it'll be one of these 3 that I'm going to show you. Okay? Is that clear? Everybody hear that? That will count as a normal part of your quiz, which is next Monday, your test, which is next Monday. So that means that on that test, you'll only have 90 points, but we'll still have a normal number of questions. So that means each question will be worth less. It'll benefit you in the long run, I think. Okay? All right, so this first one's pretty easy. It's just a thin hoop. It has a mass m and a radius r. Now, if I break this hoop into mass elements, as I've done here, I have a mass element here, a mass element here, a mass element here, and then I can go around all the way around the hoop, breaking it up into an infinite number of mass elements. Remember, what do we call those? Starts with a D. Not derivative. Those are called our differential mass elements. Right? These are infinitesimally small. They're imaginary things, but they're really small. All right. So if I just did this sort of without an integral, I would just say that I is the sum of mr squared, and then I'd add up m1 plus m2 plus m3 all the way out to infinity, and then just multiply it by r squared. Because how does r change for each of the mass elements in this thin hoop? It doesn't change, right? They all have the same radius. So that makes it quite a bit easier to do this. So I can define then dI is just going to be r squared times dm. And then if I take the integral of both sides, then I is just the integral of r squared dm. But since r and m are independent of one another, this would just be the same as saying r squared times the integral of dm. And if I take the integral of dm, that's saying I'm going to sum up all the different mass elements. It's just going to give me the total mass of the hoop. So the moment of inertia for a hoop is just m times r squared, the mass of the hoop times the radius squared. And by the way, guys, on these derivations, I'll give you the result. So I'll tell you what you're getting to, but I want to see the steps clearly laid out. Okay? Is that clear? So on the quiz on Friday, I'll give you a table, which I'll show you in just a bit, that has all the moments of inertia for all the various shapes, but I just want to see the derivation of how to get to it. So for example, on this one, you would just show this step. It would be pretty simple. It's likely not going to be this one. Okay? It won't be this one. Not likely, it won't be. It'll be one of these next two, which are more complicated. All right. So let's look at a uniform thin rod. It's rotating about the middle point. I would provide you with this figure, and I would just want you to show the derivation as it follows. So here is my differential mass element. It has a length dx. I use dx because we're working along the x-axis. It also has a mass dm. The rod has a length L, and I let my length of the rod go from negative L over 2 to positive L over 2, which will give it a total length L. You could go from 0 to L, but I think it's easier doing it this way. Then di, this is our definition for moment of inertia, is equal to r squared times dm. And so I, if I take the integral of both sides, and I'll put it in the proper units like we have here, will be the integral of x squared dm. Right, now we need to express dm in terms of x in some way. And this is sort of the tricky part in all these derivations, is knowing how to express dm in terms of your spatial variables. In this case, we're in just one dimension, so it's a little easier. But dm is going to be the mass, the total mass of the bar over the length of the bar times dx. This m over L, you might have heard this term before. This is like a linear mass density. It tells me how much mass per unit length I have. But if you're familiar with density, right, density is a volume density, right, which tells us how much mass per unit volume. Yes, density? Yeah, but this is a linear mass density, and it just tells us how much mass per unit length. So this is the tricky part on all of these, and once you get this, it follows pretty easily. So now I can replace that dm with this m over L times dx, and then my integral becomes pretty easy. It's just x squared times m over L times dx. I just substitute this in for dm. That m over L comes out of our integral. M over L, because it's not dependent upon x in any way. X squared dx. And do y'all remember how to do the integrals of polynomials? Let me show you. If I have the integral of ax to the n dx, it's going to be ax to the n plus 1 over n plus 1, and then whatever our limits are. Although in this case, what are our limits for dx? Huh?
Limit should be 1 for negative L2. And
Right. Our limits for x are going to be from negative L over 2 to positive L over 2. So we're integrating over the whole length of the bar. I'll put that in. So we have negative L over 2 to positive L over 2. right. The integral of x squared, it'll be what a will equal 1 for this particular case, n will equal 2, so it's going to be x cubed over 3. And we're going from negative L over 2 to L over 2. And let's see, I'll let you do the algebra on your own, but this comes out, I'll do it right here, let's see. So m over L, we get, I'm going to go ahead and take out this 3 that's right here. So I just get L over 2 cubed minus negative L over 2 cubed. M over 3L, what's that? L over 8 cubed, L cubed over 8 rather, plus L cubed over 8. It's minus a negative. When you cube a negative, it comes out negative. So that is L cubed over 4. And that gives us the expression 1/12 ml squared. And that's the expression for a moment of inertia for a thin rod rotating. All right, so again, I'm just going to be looking for y'all to repeat this. I'm not, I'll give you the expression at the end, 1/12 ml squared, and I'll give you the figure at the beginning that shows all the variables and how they're laid out. Y'all can do that, right? Like without much preparation? You could look at it for 20 minutes and come in? Yeah? 30 minutes? 25 minutes? 20 minutes? Okay. It'll be either this one or the next one. The next one's a little more difficult. Okay? Any questions about this?
Can I see it?
Can you see what? Oh, okay. All right. You know, y'all can move over here. You can't see. When I was in college, like every day I come into class, I sit in a different seat. Just sort of to feel like, I don't know, you get a different perspective in the classroom.
It'd be evil.
Yeah, people don't like it. They would get very upset about things. But y'all should try it. Like, I should just come in one morning. Everybody be sitting in a different seat.
It's like evil.
Yeah. All right, can I come away from this? This comes up in a lot of different applications. Anytime you're dealing with bodies and you're trying to figure out certain things about them, it's useful to be able to integrate over them. And we'll do it again next semester actually when we talk about charge distributions. Have y'all seen anything like this before? Have you ever done anything like this? Wayne, you know? No? Right, you'll see it pretty soon in calculus. Probably Calc 2, maybe Calc 3. All right, let's do the next one. Can I go on from here? All right, let's look at a solid cylinder about a rotating about a central axis. So this is a cylinder that's rotating about an axis down through its middle. So like if I was a cylinder, it would be like rotating like this. Often with these things, it's a lot easier if you can break them into smaller shapes, or your differential elements don't have to be just point particles. They can actually be like shells, or they can be, in this case, like a thin cylinder. So what we're going to do is we'll break this solid cylinder into cylinders that follow around like this. So these are hollow cylinders that have a radius r. They have a width dr, and then they have a mass dm. All right, so what we're going to do is integrate a bunch of these little cylinders moving out. So we'll have a differential mass element that's a little bitty cylinder at the beginning, and then in the middle rather, and then one with a bigger radius, and then move out until we fill the entire cylinder, the entire solid cylinder. All right. So our differential mass element then is a thin, hollow cylinder, and we'll integrate over the radius of the solid cylinder until we get the whole mass of the solid cylinder. All right. Now the density of this cylinder, which is mass over volume, the mass of a cylinder is pi r squared L. Alright, so that's just the density of the cylinder. Now, we're going to apply the definition for the moment of inertia. That's r squared dm. And then if I want to integrate both sides, I could just get I, so it's the integral of r squared dm. And then the tricky part is defining the mass element. So the mass of that mass element dm is going to be the circumference of the circle, that's 2 pi r, times the length, or the height of the cylinder, that's L, times the width of the cylinder, that's dr. All right, so this gives us the volume, I'll call it dV, the volume of our mass element. And then if we want to get the mass of it, I'm just going to multiply that times rho. It's a three-dimensional object, so in order to find its volume, I have to have 3 linear dimensions. In order to find the volume, it's the circumference times the height times the width. And that gives us the volume of that cylinder, dm. All right, and then when we multiply it by the density, that gives us the mass of that mass element. You tracking on this? You with me? Questions? Not tracking? We'll step back over through them in just a bit, okay? Alright, so that's my mass element. And then to find, I just plug that in. Remember, this is always the tricky part, is figuring out how to define dm. So, you know, you might just want to sort of go over the procedure for this, and then just, if you just want to memorize how to find dm for each of those two. I'm okay with y'all memorizing this. I think it's useful. Because you'll see it again and again, and eventually it'll sink in for you. You'll see it again in future courses, I mean, including next semester. Now I plug this back in for dm up here, because now I have an expression for dm that's in terms of r, because my mass element, the mass of my mass element does change with my radius. Because as I move out in radius, what happens to my shell? Does it get bigger or smaller? It gets bigger, right? So as it gets bigger and bigger, the mass of that shell gets bigger and bigger. All right, so now I have the integral of r squared times 2 pi r times L times dr times rho. And now I need to clean this up just a little bit. I'm just going to take everything that's not dependent upon r and take it out of the integral, and that's going to be 2 pi L and rho. All of that will come out of the integral because it's not dependent upon r. 2 pi L and rho. Then I'm left with a fairly simple integral, which is just going to be r squared, r, and dr. So the integral of r squared dr. R cubed, yes, sorry. All right, r cubed, let's see, the integral of that is going to be r to the 3 plus 1 divided by 3 plus 1, or r to the 4th over r. My limits of integration here are going to be for what? I'm integrating over all these shells, beginning at the middle and moving out to the edge. What's going to be my limits of integration for this interval? This is really exciting for y'all, isn't it? Like, I remember in college, I really liked this stuff. We did this a lot, like in electricity and magnetism. I can tell that y'all are just as excited as I was. What's that, Andrew? Oh, okay. I think so. What are my limits of integration for this? 0 to r, right. So I'm moving from the center out to the edge, which is 0 to r. Remember before, we were going from negative L over 2 to positive L over 2. So your limits are going to be different depending on your situation. They're not always 0 to something. 0 to big R. So that's going to be 2 pi L rho r to the 4th over 4. All right, but then I can simplify it and put it in terms of m and r squared. Let's see. I have this expression for rho up here, so I'm gonna put it in down here for rho. So I have 2 pi L, rho was m over pi r squared L, times r to the 4th over 4. Let's see, so I get an r squared out here, and that becomes squared. I get rid of my pi here and here, my L there and there. I have a 2 there, so that becomes a 2. And I'm left with 1/2 mr squared. So if I want to know the moment of inertia for a cylinder that's rotating about its central axis, it's just going to be 1/2 mr squared. What's that?
I can't tell what any of that says anymore.
You could sit over here.
LL, I see a bunch of marks on.
All right. Let me step back over both of those, okay? And I'll put this online as well, so you'll have it. I'll give y'all a second to finish. So on Friday, I'm not looking for rocket science. I just want you to be able to reproduce both of these, or one of these.
What's
Okay.
the difference between using the small lowercase r and the big r?
The lowercase r is one that I'm integrating over, so it doesn't have a set value. I'm letting it go from some value from 0 to big R, and uppercase R is the actual value of the radius. All right. So what you'll get a sheet of paper. It'll have a table on it, which you probably see in your book already. It's on the next page. That'll have all these expressions for these various things. So you'll know what the answer is going to be, but I'm going to be looking that you can get the steps for derivation. I'll be looking particularly that you get the dm correct, and that you apply it properly. I'll be looking at your limits of integration. Where is it? Here, limits of integration. That you do this integral correctly as well. Just review. Go back to the. So I have this uniform thin rod that's rotating about its middle. I'll already have this figured for you, so you'll know what the limits of integration, all that jazz are. You start with your definition of moment of inertia. I is the interval of r squared dm. In this case, our relevant variable is x, because that's our whole body lies along the x-axis, so it's x squared dm. And then you have to figure out, well, what is the mass of this little mass element? And in this case, it's going to be the linear mass density, that is the total mass over the total length. That gives me how many kilograms per meter are there in this, times the width of my differential element, dx. So that's dm. And then you just plug that in for dm, and you take the integral, and then you're basically done. So here you put m over L dx there. The m over L is not dependent upon x, so it comes out of the integral, because it doesn't integrate at all. And then I take my limits of integration from minus L over 2 to L over 2 of x squared dx. Gives us this. And then put in an L over 2. This is just algebra here. Okay? I'm not terribly concerned about the algebra. Even if you didn't show the algebra, I wouldn't be upset. But I do want to see all these other steps. All right, 10 points, I think. So it should be an easy 10 points for the test. Remember, this is going to be part of your 100 points, but it's like in 2 parts. That makes, as I said, that means that your test can be a little bit longer, which I think y'all like, right? You like for the test to be a little longer. That way the questions don't count as much. Is that not true, Eddie?
Oh, I don't like long tests.
Oh, okay. Not long, but normal. Yeah, Chris?
All right, a non-mathematical kind of conceptual term.
Mm-hmm.
What is that 1 over 12 ml squared as it relates to that figure? What is that?
What does the M and the L mean?
You know, just like what is the inertia? What is that?
It means how. Remember how when we talked about inertia in terms of linear motion, the inertia was, well, how hard is this thing to get moving? So like if you have a huge block, it's very difficult to get it moving. And so this says that if I have something with a big mass or a big length, it's going to be a lot difficult to put it into rotational motion. All right. but it's more important is the length. So if I have a really long rod of a certain mass, it's going to be a lot harder to start rotating than a shorter rod of the same mass. Does that answer your question? I'm not sure that's exactly what you were asking.
Yeah.
So will that always be the formula for any rod?
For any thin rod that's rotating about a central axis, yes.
Or is it just that because of whatever you did? I don't even know.
No, these are generic formulae. So they're always, anytime you have a rod that's rotating about its axis, which is actually actually fairly frequent. Yeah, really in real life, if you're ever dealing with these, you're not going to need to know how to derive this, right? But it comes up, sometimes you might have shapes that are different, that, aren't in a table, and then you would have to derive this. Really, I want y'all to know how to do the method of integrating over a body, because it comes up in other scenarios. So it's really a mathematical tool that I'm concerned about, that y'all can integrate over a body, over these two particular bodies. All right? All right, so that's a thin rod. Let me just review recap the cylinder. Yeah, John? What's that? One of them, yeah. So there'll just be one of them. It'll be one of these.
Oh, this would be one of them.
Yeah.
So then who counts?
I don't want it to be difficult. Huh?
So then who counts it out also?
No, the thin hoop. There are really only two. The thin hoop, y'all can do that right now. It's pretty easy, right? Because M and R are the same as M R squared.
So it's gonna be one of these two.
Every one of these two.
And everywhere else.
That's it.
That's it.
Yeah.
So you memorize what we wrote.
Huh?
I memorized what we wrote for these two.
Yeah. If you just memorize it, I'm okay with that. Because I think eventually it'll sink in. But it's really better if you say, well, I need to integrate over dm and remember what is the mass element dm. I want to get it from your brain to the sheet of paper in some way. All right. I understand that most of you might just look at it right before and try to geek it out. No? No. All right. Okay. Now this is going to be an addition. We will have a quiz next week too. So.
What if, let's say, where you got where you try to describe the differential mass, that shaded rings, let's say that was a hollow cylinder. So you would differentiate from the radius of the inner circle to the radius of the outer circle, like integrate over that distance. Let's say that where you got it shaded.
Hey guys, you guys. Yeah, correct.
So where you got a shade of that. It was hollow. All right, like the cylinder's hollow, like a pipe. Like, follow me?
Right, it is like a pipe. Yeah.
Okay. So if it's hollow, let's just say it's hollow. It's got so much mass, and then the inside is empty.
Right.
And it's rotating about the same axis.
Oh, like if this was hollow?
Yeah. So
Okay.
the integration would be from whatever the radius of the inner diameter to the radius of the outer diameter. Just that.
Yeah, in fact, let's see, how would that work out? So,
I'm asking weird questions, but I'm not.
no, they're good questions.
So instead of from 0, it would be to whatever that inner diameter would be to the outer diameter.
Right. Mm-hmm. Yeah, if it was just a pipe, right, it would just be from the inner to the outer diameter. But in this case, we're doing a whole cylinder, so it's solid all the way down to the middle. So that's where our limits of integration come in here from 0 to R. So your pipe, as you call it, this hollow cylinder, it's like a pipe, right? That's your differential mass element. And you're saying, I'm going to let that pipe get bigger and bigger and bigger and integrate all the way out to the outer edges and then add up the moment of inertia with my interval. So your mass element doesn't always have to be just a little piece. It can be a little shape, like a shape, in this case, a thin hollow cylinder. Sometimes when you get into this in Calc 3, you'll use actually thin spheres and all sorts of different shapes for differential mass elements. They're not just little pieces. They can be different shapes as well. All right? That's kind of exciting, right? I don't want you to think that this is too important, but it is important because it's a useful tool. And I don't. That's why I'm taking it out of the regular test because you're really just sort of memorizing stuff, and I understand that for most of you. But you'll see it again, and at some point it will sink in to you. All right. And I think it's kind of fun, like these things, like looking at a problem like that and thinking about what is the differential mass element, and how do I define the mass in terms of density and position and what have you. Right? Like you could go this afternoon and do it for fun. Sure. You and I have different.
This would your kids think you're a little your kids think you're
They think I'm like the
interesting.
coolest guy in the whole world.
Is that what you believe or what they believe?
No, they think that's true. I mean, they'll think that too, right?
Yeah.
Pretty cool guy. Maybe not in the whole world, but or maybe in this room. Right? Yeah. All right, so no, I'm not cool. So maybe among the faculty of my department. Am I cooler? All right. Now you will have this table. So this table, in reality, like if you're doing this out in the real world, you just pull up this table. But so this shows the moments of inertia for all these different objects. So for example, here's a thin rod. Here's a cylinder of radius r. That's one we did. And here's the hoop. So you'll have these three things. But then I also include these other things. You can do these derivations in a similar way. We're not going to do them here. Some of them aren't really that much more difficult, although the cylinder of radius r, this one is actually quite a bit more difficult because it's around a different axis. But you could probably, if you worked at it for a couple hours, you could probably derive these as well, figuring out how to do the derivations for these moments of inertia.
Now, do you just plug in things or will these be sums?
No, these are just, if you have the mass and the radius, you just plug in the numbers. Right, so these derivations have already been done. I'll show you an example right now. All right, so these are just different shapes, rigid bodies, and that's how you determine their moment of inertia. Remember, the moment of inertia, I, is equivalent to what that we did in linear motion? Not momentum, no. What was our measure of inertia in linear motion? What variable described the inertia of an object? You probably won't find it in your notes. Mine, y'all think. Remember, inertia describes how difficult it is to move something. And if I have an object moving in a straight line, what about that object describes how difficult it is to set it into motion? It's mass, yeah. So this is the equivalent of mass. So, actually, you probably could have found it in your notes. So, back here, where was it? So our moment of inertia here is equivalent to our mass, right here, in our rotational, moving from a linear frame to a rotational frame. All right. Let's see, Ooh, I don't think I brought that, but I think I can find it on the internet. Please check.
You should have this like connected to a cloud or something.
Yeah, I mean, I have SkyDrive. I could put it all on SkyDrive. But no, I don't have it. I'm going to find it on YouTube. It'll just take me a moment. So I'm amazed that his Walkman doesn't fall out of his pocket. Like he has a little Walkman in his pocket, and when he spins around, it doesn't fall out. I think they probably had it.
I think that kind of dates the movie itself.
That he has a Walkman?
Yeah.
Yeah.
Like Fruitopia and Independence Day.
Right. Okay, so we can look at this. We have this guy that's rotating about on a hoop. So the wonder wheel is basically a thin hoop like we've had. And we know the moment of that, right? The moment of inertia for a hoop is what? Right, it's just mr squared. So I of a hoop is just the mass of the hoop times r squared. That's the radius of the hoop squared. And what about Richard Pryor? we can treat him just as a cylinder. So we'll treat him as a second shape. He's basically a cylinder, because he sort of has his arms and legs up. And so we're pretty cylindrical in shape, actually, if we're extended out like this. So you could do it in a more complicated way, but we'll just treat him as a cylinder. Now, we have two cylinders up here. We have a cylinder that rotates about this body, about that axis, and then we have a cylinder that rotates about that axis. Which one do we use? Right, we use the second one, because he's rotating about an axis through the middle. Yeah. Notice that the moments of inertia are a lot different. For which is the moment of inertia a lot bigger? The first or second? The second one's a lot bigger. And that's why it's a lot more difficult to spin in this direction, by doing cartwheels or front flips, than it is to spin through this direction. I mean, anybody can spin on this axis, but it's very difficult to spin on this axis. And that's because your moments of inertia are a lot different. All right, so we can find the moment of inertia of a cylinder as a quarter m squared plus 1/12 mb squared. Quarter mr squared
Plus 112 MB squared.
mb squared. All right, so we'll say the mass of the hoop. Let's do some. Oh, let's see, I have it here. So we assume a mass of 100 kilograms. That's for Richard Pryor. His radius, we'll assume 30 centimeters. That's the distance from the center of his body out to here, so 0.3 meters, and a length of 2 meters. So if we put those in, the mass of Richard Pryor is that's the hoop. Let's say for the mass of the hoop, we'll have 10 kilograms. The mass of Richard Pryor will have 100 kilograms. The radius of Richard Pryor will be 0.3 meters. So if we describe him as a cylinder, what is that radius? About 30 centimeters. And the height of Richard Pryor on this cylinder, that's going to be this length, which is B, the length B. So we'll take B to equal 2 meters. And then that will also have the radius of the hoop will also be 2 meters. All right, so we can calculate this. We'll have the total moment of inertia will just be the sum of the hoop plus the cylinder. And the hoop is going to be 10 kilograms times r squared, which is going to be, the radius of the hoop, I'm sorry, will be 1 meter, which is half his height, times 1 meter squared, plus the moment of inertia of the cylinder, which is going to be 1/4 of 100 kilograms times 2 meters, or no, I'm sorry, 0.3 meters squared. That's the distance from here out to his shoulder. That's his half his width, or his radius, plus a 12th mb squared, which is going to be 100 kilograms times 2 squared. All right, so if I have multiple shapes that are connected and rotating, and we'll see this in some example problems next time, you just add up the moments of inertia for all those shapes. So that's 10 plus 100 times 0.3 is 25 plus 2.25 plus 33.3. I get 46 kilogram meters squared. All right, so that's my moment of inertia. The point being there is that if you have multiple shapes that are coming together and they're rotating at in the same body, like here I had a cylinder and then I had a hoop that was around him, then you just add up their moments of inertia. And we'll see that in a problem, like I said, in the homework, I think, and also some old exam problems. All right, I think that's all the time. Sorry, we're a little late. Y'all have a good day, okay? Friday, okay?